This is Physics 2211, Lab 2, Motion of a Falling Object. In this lab report, I will first introduce the experiment and then explain its three components: the tracker analysis of a physical object and the two computational models, one that accounts for only gravity and one that accounts for both gravity and drag. I will then follow with the results and the discussion. The purpose of this lab is to investigate the downward motion of a falling object with reference to the forces of gravity and drag. I will do so by comparing the tracker analysis of observed motion with the predicted motion from two computational models. The fundamental principles in this lab are Newton's second law, gravity, and drag force. Newton's second law states that F net is equal to the derivative of momentum with respect to time. From this equation, the following velocity and position update formulas were derived. They will be used in this experiment to predict the downward motion of the falling object as a function of time. Gravity, or the weight force, is the vector 0, negative mg, 0, where m is the mass of the object and g is a constant to represent acceleration due to gravity, equal to 9.8 meters per second squared. Because gravity points down, the vector is in the negative j hat direction. Drag force is the force acting opposite to the motion of a moving object with respect to a surrounding fluid. The direction of this force is positive j hat. The gravity and drag force added together is the net force, and terminal velocity is when the drag force and gravity are equal but opposite, meaning that the net force is 0. Then, by Newton's first law, velocity is constant. I will be using a cylindrical container to drop from rest. Tracker will be used to extract time, position, and velocity data, and the initial conditions found will then create the foundation of the computational models, which will make use of the principles and formulas outlined above. The main result of this experiment is that the computational model that account for gravity and drag was significantly more accurate than the graph that only modeled gravity. This suggests the presence of a drag force on the object would decrease its downward acceleration. The initial conditions from tracker are noted on the slide. The system is the medicine bottle, and the surroundings are the ground, air, and everything else around it. I define the axes as positive x to the right and positive y upwards. In this case, because the medicine bottle moves downward, it is moving in the negative y direction. The key assumptions of this experiment is that Fd is always proportional to velocity squared for the computational model that accounts for drag. Also, it is assumed that there is motion only in the y-axis. The first computational model does not model drag, only gravity. The initial conditions were set as outlined in the previous slide, and B, the proportionality constant for the drag force is set to 0 because we are not accounting for drag in this model. The while loop runs until t is less than 0.25 seconds, the last frame in the tracker analysis. As seen on the slide, the gravity, velocity, and position update formulas have been modified accordingly into Python code to allow for the iterative prediction of the motion of the medicine bottle. The second computational model is extremely similar to the first model except for the inclusion of the drag force through a non-zero proportionality constant b. The initial conditions are identical except for the value of 0.6701 for b, determined through trial and error until the same final position was modeled at t is equal to 0.25 seconds as was observed in tracker. The equations used are as seen on the slide. The resulting graph shows the observed motion and both graphs of the predicted motion. They are initially similar but begin to deviate quickly. The computational model without drag noticeably overestimates the object's position and velocity, and the velocity decreases at a constant 9.8 meters per second squared. The computational model with drag, however, is much closer to the graph of the observed motion and shows the curve flattening around 0.15 seconds, indicating terminal velocity, where the drag force is equal but opposite to gravity, leading to a constant velocity and keeping it on track with the observed motion graph. For the what if and what does it mean questions, the model with drag can predict a terminal velocity as the graph in the previous slide begins to flatten around 0.15 seconds, indicating a terminal velocity and a net force of 0. The computational model without drag cannot predict a terminal velocity because you need the drag force to be equal but opposite to the gravitational force to reach terminal velocity. Obviously, since we do not account for drag, the other model cannot predict this. For the second question, if we threw the object downwards rather than dropping it from rest, we would still reach the same terminal velocity because it is only dependent on the drag force and independent of the initial velocity. Using the model with drag in a scenario where the initial velocity is 0, negative 30 meters per second, the graph seems to flatten earlier at 0.10 seconds. This suggests that the time taken to reach terminal velocity may change. Potential sources of error in this experiment may be from human error due to the inability to select the middle of the object consistently in tracker. There may also be an accumulation of rounding error in the GlowScript model that makes it seem more inaccurate than it is. The calibration in tracker could also be slightly inaccurate, and the drag force was determined purely through trial and error and is not exact. Overall, in conclusion, all three graphs were similar in that they predicted acceleration in the negative y direction. However, the model that corrected for drag was much more accurate than the model that only accounted for gravity. This suggests the presence of a drag force on the object would decrease its downward acceleration.